Hey, Jara. Jara, is that how you say your name?
Yeah, it's Jaren.
Jaren. Is that your baby?
No, it's my godson actually.
Oh, nice.
hmm
Oh, that's great. Let's see. Cute kid. I guess all kids are cute. Hmm. Hey, guys. Um, let's see. I was going to go over, power, start with power consumption today, but I want to talk to you guys a little bit about project one. I haven't really started grading them yet. Any thoughts on the project? How did it go?
I didn't think it was that bad, but the noise margin thing was a bit tricky until you sent out the email.
Yeah. I get confused about the noise margin too myself. So I wanted to talk a little bit about that today, sort of
I had to get kind of creative on that too. Like in order to obtain it, I had to like create a line and like move the line to the transient points of the graph,
I see. Okay.
and then like use the cursors. Like when the cursors reflected a -1 slope, then I took the values and did some quick calculations to determine what the noise margin was.
Okay, cool. Does the whole concept of noise margin kind of make sense?
Oh, absolutely. I
Yeah.
think it makes sense.
Okay. Let's see.
It's like a tolerance, right? Like, and within that area, like that's as where you can get that 1 or 0 still within those, that tolerance.
Yeah, yeah. It's kind of like reflects your immunity to an error coming into your calculation. So I was going to talk about that a little bit because one, there's just the definitions are a little bit confusing. So I wanted to make sure it's clarified. But the other thing I wanted to talk about is, why are we talking about it? What's the important thing about this noise margin? And I was like struggling with how to talk about it. So my explanation got more and more, started going down a rabbit hole of reliable communication and calculation. So, but anyway, so I thought this might end up being a little bit of a rambling, even more so rambling than normal, but hopefully it'll mean something. It'll help clarify something, because I think errors in communication actually happen. Like if you guys get, and I hope all of you do, will be one way or another involved with some kind of microelectronic hardware, whether you guys are computer engineers and you're using a high-speed microprocessor, or you're programming an FPGA or building a chip or whatever it is you're doing, sooner or later you're going to end up trying to debug some communication, some signal integrity or communication problem, some error that's going to come in getting data from point A to point B, or some error in the calculation because of a lack of noise margin under some operating parameter. So I wanted to talk about that to begin with. So I don't know, has anybody in this group not heard about a concept called the bit error rate? Have you guys heard about that concept? So anybody heard of it? I don't know what classes you guys have taken, what you haven't. So
No, I don't think I've heard of that before.
no,
Yeah, me
okay.
neither.
So it's
Heard of
more
bit
like it's kind of a telecom concept. It's really pretty straightforward. It basically says if you have a certain, and it's usually comes, let's say if you have a fiber optic channel or something, it usually comes in a channel. That's usually where it's defined, is from A to B, or you're communicating from a mainframe to another mainframe. It's basically you how many bits do you transmit before, it's the inverse of how many bits you transmit before an error creeps in your communication. Okay, so this is like typical bit error rates are, this is something might be 10 to the minus 6. It's unitless because this like a 10 to the minus 6 bit error rate says every million bits you transmit, you might get one error, or you might have 10 to the minus 12, 10 to the minus 16, 10 to the minus 21, I don't know, whatever. And different communication networks have different requirements on bit error rate. Now, this is the most fundamental, the most fundamental aspect of getting an error when you're transmitting a bit from point A to point B comes from your signal to noise ratio. Okay, so if we look at the signal that does not have a very large signal to noise ratio, it's going to look like this, right? So this would be, this would be a 1, and this would be a 0. So this is like time. This is voltage. And, it's not unusual if you had like, I don't know, a real, like a fiber optic communication or cellular communication, whatever, to have a very low signal to noise ratio. So in this case, this thing here, this stuff would represent noise. And this value looks like a signal, voltage, whatever it is. It's got a bunch of noise on it. The reason it looks so bad is typically, this delta V here, by the time, let's say you're doing a fiber optic communication, whatever, this delta V might be, I don't know, it might be like a millivolt or something coming out at the end of your channel. It's funny, as an aside, we have a couple who does they work on GPS signals over in JPL. And I really don't understand GPS signaling, but what they were saying is their signal to noise ratios are usually much smaller than 1. So that would mean that your noise is much higher than your signal. And I just I don't get very far in trying to understand how they sort of calculate that. So I don't know. So okay, so this is like what you end up with. Let's say at a generic communication channel that has a low. This is like a low signal to noise ratio. So just eyeballing this, I don't know. This might be like a 5-to-1 or 3-to-1 signal to noise ratio or something. Okay, so in this kind of scenario, typically when you see this is, again, I'm really trying to go generic, don't get too wrapped around. If you guys don't have the background for this, it's been a while since I studied this myself, but sort of when you see something like this, it usually means broadband noise, okay? And broadband noise, if I sort of, it has a, typically it's modeled as having a Gaussian probability distribution function, okay? Does any of this stuff sound familiar or just, it's like way off? No? So anyway, let me just talk about, so probability distribution function of Gaussian noise. Gaussian noise is like when you have broadband noise means that the frequency of the noise is in any voltage. It's the noise. The noise's frequency can be like in sort of any frequency. It's not low frequency, it's not high frequency, it's like sort of broadband. This is like the most fundamental case. And so what it says is, if you look at the distribution, so if you look at sort of the histogram of noise values, and it's centered around something. So let's say the noise is centered around some value, it'll have a certain distribution function. That means like, and then this is where you get, 1 sigma, 2 sigma, and 1 sigma is like, this is actually, 1 sigma is kind of more like this, I think. So this is like, basically it says 0.67 of your signal values or around this amount is 1 sigma away from your mean. Okay, but the key thing I'm trying to say here is a Gaussian curve. Are you guys all familiar with Gaussian curves?
Yes.
Yeah.
So the key thing about a Gaussian curve is this sort of goes on forever. It gets really small, but it goes on forever, meaning that if this is a Gaussian curve and I'm going to try to draw it around there. So the noise will look like kind of like that. If I was gonna, the noise will have a certain value, and it says a certain mean value, but meaning the noise can go all the way. Some bits will see a noise that's gonna do like that. Okay, because that's sort of the tail end of your Gaussian, and you're out 9 sigma out or whatever it is. 9 sigma or 6 sigma or whatever is like, I don't remember what 6 sigma is or 9 sigma, but it's like 99.999 is within 9 sigma, but that just means that the next digit is outside of 9 sigma. So means that every once in a while, like if you're transmitting, if you have like 1 million events, in those 1 million events, there's a possibility you'll see a noise spike that's very large, larger than you expect, and it'll give you a bit error. So in this case, if you had something looking at this, it would momentarily see a 0 coming out during this one. And if this was a clock or something, it would just blow up your circuit, blow up your communication. So this is kind of the most fundamental way where you look at bit error rates or communication failures. And so this happens a lot again in internet communication, etc. And what people do, because you're always trying to get your signal to go further, faster, etc. We have a lot of methods of actually embedding error coding into our signal. So basically you're doing CRCs, you're doing Hamming distances, you're doing different types of, there's different kinds of error coding in your packet switching networks and so on and so forth. And so you basically are, you have enough error coding that in your overall end-to-end system that says, okay, if every billion bits that I transmit, I get one error, I can correct it. Okay, now every billion bits sounds like a lot, but remember, we're downloading, if you're downloading a video signal, it's like a gigabyte. So like there, if you had like 1 × 10⁻12 bit error rate, you could potentially get a lot of errors in that video. And an error, if you were not thinking about how to correct for it properly, it wouldn't mean just like you would get a grainy pixel. I mean, it would, because you have an MPEG format in that video, it could totally wreck your everything, depending on how much system level things you have there to make sure that doesn't happen. So anyway, the upshot is, at the most fundamental level, you could have errors in transmission of signals, and like you do things to try to correct for it. Now, this brings us to our, what we do in a microprocessor or FPGA or these chips we're talking about. Because, one question could be, well, hey, why are we using 1 volt? Why not just use, 2 millivolts as our power supply? We're going to talk today about power consumption. And, earlier we talked about high electric fields and stuff like that. It seems like it would be good to have lower power supplies. So why don't we just sort of crank down the power supply lower and lower and lower? But the fundamental reason, there's more reasons, but the fundamental reason I look at this thing is that you would have a similar issue in your digital communication on chip or in your calculations, which is the same thing. Let's say if you're adding 2 64-bit numbers together, you could end up with an error in that calculation if you had this signal to noise ratio. You have the same type of thing. An error could, at the most fundamental level, you could get, this broadband noise, you could get this errant signal coming in. And so it would mess up your calculations. So, but there's a difference. Okay, there's a difference between stuff you do on a chip or in your FPGA or microprocessor and a sort of internet, Ethernet communication channel or a wireless communication channel. Basically, typically you do not have any, especially inside the chip, you really don't have any error correction. Okay, so if any error does come in, you're typically not doing CRCs or anything. You're just, your adder, your multiplier, your processor, your memory access, all that's happening, and there's no correction. If you you make a mistake, it'll just be a mistake. And it's kind of could be really bad because that mistake could happen not just in a, ALU or something like that, where it messes up your calculation of some data that's going through your circuit. It could actually happen in the control of your circuit. So if it happens then, it could put your chip in some weird state that you won't be able to recover from, that you'll actually have to, I guess this does happen sometimes, your system will crash, right? It just doesn't know what to do. It's in some weird mode. And, that does happen a lot, unfortunately. I think things are much more robust, and maybe you guys don't have as much experiences with system crashes and stuff, but especially when you're building your own systems with your own software and your own hardware, you see system crashes, more. So, okay, so what happens? So now the thing is, in a typical chip, imagine the kind of bit error rate you need not to get errors, because, we said you have 20 billion, let's say you have 20 billion transistors or gates. I don't know if sort of gates. Let's say just a small percentage of these, let's say like 1 billion gates are operating at a particular point in time. I don't know how realistic this is, but it's possible. It depends on power consumption. And let's say your clock is, gigahertz. Again, none of this is like unusual or crazy or whatever. It could be happening. So if 1 billion things are switching 1 billion times a second, that's like 1 times 10 to the 9th times 1 times 10 to the 9th at like a real brain dead calculation level, or 1 times 10 to the 18th bits, or something is happening per second. Okay, 1 times 10 to the 18th, I don't know what that number is, but pretty big. So unless you have a very, very, very small bit error rate, like, I don't know, like every hour, every 24 hours, whatever it is, something really terrible is going to happen to your system. It's going to crash. You're going to get, well, the errors could be big or large, big or small, sorry, but some bit would get flipped, okay, where you don't want it. And imagine that would happen again in your Tesla's microprocessor as you're driving around. I mean, unfortunately, it does happen from time to time, right? And they're like, or your computer crashes and whatever. But the upshot is that the bit error rate in your chip, in these digital communication or digital circuits, microprocessors, whatever, have to be much bigger than the bit error rate that's in your Ethernet connections or whatever, because there is no correction built in. It is what it is. So what we want is a really robust one and a really robust 0. So, you know, if this is like your communication channel, I want my chip to look like, you know, this, and I want the noise to be like whatever, like that. If you know, if anything, right? I want the noise to be teeny tiny compared to my signal. I just do not want, again, this is at the most fundamental level. I do not, like, even if there's a distribution here, I want the chance of this one being represented as 0 to be so small because I just have too many of these events happening. So at the most fundamental level, this is what our noise margin is protecting. It's the noise margin says, more or less, it says that here is a 1 and here's a 0, and I have a very big gap between those two signal levels. That's kind of at the 30,000 foot level what a noise margin is telling us. Now, on top of this very fundamental noise level, when you're talking about real circuits, you have a lot of other noise creeping in. Okay, so you have, there's, again, this is like a fundamental noise. If everything was running off of the cleanest power supplies, you had the most beautiful packages, there was no inductance in any of your lines, everything was beautiful, you know, this would be sort of a fundamental noise that you would be above, and your noise margin would have to be above this. But the reality of the situation is it's a lot uglier than this. Okay, so besides this broadband noise, you also have a lot of environmental noise. Okay, you're working on your computer at home and you're, you know, in an older house, like my house is from like 1947. Every time the air conditioning kicks off, the lights dim a little bit. So that's like a glitch that if you know, could end up crashing your computer, you never know. And sometimes, you know, sometimes we're, again, this is our home. We live in the boondocks, an older house. And like, until you put a uninterrupted power, UPS, whatever that stands for, uninterruptible or uninterruptible power supply on the, like the cable box, we constantly, you know, our Ethernet goes on and off, especially with like in the summer where air conditioning is kicking in. This is all environmental noise that's messing up the bits, messing up our cable box, and that's like all these digital calculations that get messed up. Or I don't know what examples I want to use, but there's a lot of environmental noise. There's a lot of noise just in the way you build your circuits, just the thing operating by itself. I don't know if I've mentioned this or not, but if you guys ever played with, you know, FPGAs or FPGA boards or microprocessor boards or any high-speed digital board that you have access to in the lab. Again, I hopefully, I don't know if, well, maybe you guys will go back in the lab next semester or whatever, but if you just probe any point, or if you just have one thing you can do, which is a really bad, this is very scary, is if you just take your microscope probe, next time you guys are in the lab, do this. So this goes to your microscope, not microscope, sorry, oscilloscope. So it's your oscilloscope probe. Your ground, just hook up your ground to clip it onto the tip. Okay, so this makes like a pretty good antenna right there. So I just hover it around your board and see how much electromagnetic interference is, so what kind of signal this just picks up that's just being, sent into the world by the board itself. And you'll see some horrendous, tens, maybe 100 millivolt of noise just sort of emanating everywhere, just from electromagnetic interference. And so anyway, upshot is the actual noise situation in a real world environment for digital circuits is much, much worse than this broadband noise thing that we're talking about. So all that means is you need a very high noise margin. Otherwise, you're going to have errors in your calculation or communication in your digital circuit. And usually you have not built in any protection in your system about that. And the reason usually you don't build up error correction usually is because there's a big overhead of circuitry and a big overhead of time. There are places in your chip or in your FPGA or so on that you do typically put in error correction. And those are in your high-speed serial input and outputs coming out of the chip. You might have it in your DDR memory access, things like that, which are like very specific communication circuits in and out of your chip, might have built-in error correction just for this reason, but typically your stuff inside the chip, like if you're accessing memory inside the chip or you're doing some calculation, will not have any of that. So things get, so basically that's the idea behind noise margin. Like it is very, very important, and you will, so as an aside, a lot of the most fundamental engineering you'll do when you'll maybe you'll remember this some night when you're in the lab pulling your hair out at work, is when you're designing a lot of stuff in your design flow is already put there to protect yourself from issues. So let's say you're designing an FPGA system. Are you guys familiar with FPGAs, by the way? I'm assuming there's a lot of you guys that are computer engineers.
Yeah.
Okay.
Yeah.
Well, let's say you're doing that. Most of your work is going to be, looks like kind of like programming. I don't know how you guys think about this, but you're writing Verilog code or VHDL, and you're synthesizing it, and that there's a whole flow, and it looks like you can somewhat ignore these kind of things, and usually you can, and there's a lot of that flow, that design flow, and a lot of what, say, Xilinx or whoever FPGA provider is that you're using, a lot of their activities has gone towards this stuff being opaque to you, okay? But where you will see this stuff is sooner or later, you'll write your code, plug it in, and for some reason, FPGA 1 is not communicating with FPGA 2, or for some reason, at some clock speed, your memory access is like no longer working. So where you end up with these things usually is when you're debugging something that's just not working. It's supposed to be working, but either because you have, and again, we'll look at the stuff, a little bit of detail in your further projects, which are going to build on this project, is you'll see how noise, etc., creeps in, and it happens all the time in the real world. And where it happens is when the stuff's come back or systems built and you're like debugging and you're going, why, this memory was working before, now when I put it on a separate board with a connector, now it's not working anymore. Why is that? Or I'd worked at a certain clock rate, but even though it's specified as spec at this clock rate, it's still not working. or, you know, I made this cable and when I plug the cable in, it doesn't work. So a lot of that stuff, you'll come back to these concepts of noise margin and correcting for noise margin, et cetera. And I think that's when it'll kick in. Now, the concept of noise margin by itself, like the way it's defined, so it's sort of taking all this to an inverter or an inverting logic gate. So you have V in, and you have V out, and you have the curve like this in a CMOS circuit, or ideally, if you had the absolute ideal gate, it probably look like, kind of look like that. And basically, noise margin is, I always have to look this up, is the sort of the VOH is the highest value of an output bit, and VOL, VIH is the sort of the lowest value that you would still recognize as a one. So basically, this is the idea. Sorry, I hope I don't confuse you guys. What you want to pretend is, when you're looking at noise margin, is you're pretending like you're driving a inverter or your inverting gate or whatever it is with an exact copy of itself. So you're sort of so it's like a two circuit concept. So this is why it gets confusing. It's like you want to kind of compare this input to its own input or output or something like that. But just, it's a two circuit concept in the sense that you want to make sure that whatever this guy is outputting is acceptable to itself as a proper input. So if this guy is the lowest, the worst case output high value that it's outputting out of here, okay, so it'll be on this axis, right? This is the output axis. So its worst case will be here when the slope goes to -1. Anything beyond this thing is not considered a good one anymore. Okay, so that's VOH. And you want to say, you want to compare that to what's accepted on its own. I mean, again, this guy is exact replica of what's Senate. What is the highest, or sorry, what's the lowest value? Now this is the input, which this guy still accepts as a 1 coming in, and that's on this input axis. And that's why, like, this noise margin high says this is the worst case 1 that I'm going to transmit, and this is the worst case 1 that I accept as a 1 being as an input. So, and so that's like noise margin high, and the same thing is true for noise margin low. So you have to think about this output going to this input, and for a 1 and for a 0. And so the noise margin is what's the worst case 0 output I have here to what's the worst case 0 input I take, accept as a 0 here without messing up the communication. Does that make sense? I hope it, I don't know if I'm just maybe confuses you guys more, but so any questions about that? No? Okay.
Not so far.
Okay, so we'll just leave it at that. Okay, so noise margin, and again, what we're gonna do with the projects is, again, with the projects, I'm trying to give you guys, and step by step, hopefully we'll get there. So like the next project I'll have for you guys on Thursday is we're gonna make this, you built a communication channel in your project one. We're gonna make that more and more realistic as a communication channel between two chips. And the reason we're gonna be looking at that is, one, I think a lot of you, even if you don't go into chip design, you're gonna be seeing chip-to-chip communication. And unfortunately, most of you, therefore, will have to end up debugging chip-to-chip communication, because that's where, especially where a lot of things go wrong because of these communication errors. Okay, so we'll come back to all of this in a bit. But so the next thing we're going to cover, this is moving to slide deck. So we talked about the speed transfer function of CMOS gates. So those are, again, we're kind of hitting some of the same concepts, reliability of communication, it's a figure of merit. Speed of calculation or operation is another figure of merit. And then we said power consumption is also a figure of merit. And this is turning into, more and more of a figure of merit as time has gone by. And it might be the driving thing right now in terms of this trade-off between power consumption and functionality, or power consumption and speed of operation. It's really, power consumption is really driving. It used to be kind of a factor, it might be like the factor right now in deciding our chip architectures or system architectures and so on. And we're going to talk about a few different concepts. So first, it's to look at power consumption. It's a little bit confusing because we need to look at both power and energy. The upshot of what we want to look at is power consumption, but power itself is sort of how should I put it, is a continuous concept. I mean, there's an instantaneous power. So when we talk about power, this is power at a particular point in time. But when we look at a CMOS inverter, remember that when the inverter is sitting without switching, there is no power consumption because, well, there's no dynamic power consumption. But so let's say this guy's off. So in this case, there is no instantaneous power consumption, but as this thing switches, I'm charging and discharging this load capacitance that this guy has, and this capacitance could be other circuits, it could be anything. And the way I translate this charging and discharging, I have to take an intermediate step to look at the energy of charging and discharging this capacitor per operating cycle, and then translate that to an average power. And we'll see why that is, but that's sort of why we look at both power and energy. Ultimately, what we're looking for is an average power consumption. And the reason we want to looking for an average power consumption is instantaneous power consumption means, that particular nanosecond, picosecond, that was your power consumption. But what does it mean for, how many minutes your cell phone can operate? Because it's changing. That power consumption is changing with time as you're doing different things, as your circuit is doing different things. So you have to look at the average power consumption over some reasonable amount, whatever is the interesting amount of time. It depends on your system operation. And then So we're gonna be looking at, there are two types of power consumption. There's the dynamic power consumption, means the power consumption when your circuit is switching. And we've hopefully have made it clear to you guys that the most attractive thing about CMOS to begin with, and still is, that, well, to begin with, was that there was, for all practical purposes, the only time the circuits would have power consumption is when there'd be switching activity. So if the circuit wasn't doing anything, there wouldn't be any power consumption. And that was, enormously attractive compared to circuit families where there was power consumption, even if you weren't doing anything. But with time and with, as we've gone to more and more density of transistors per chip, meaning we've gone into smaller and tighter processes, the static power, which is the power consumption when nothing is happening, has also gone up. So unfortunately now we're in a situation where there is a significant amount of power consumption happening even when the circuits are not switching. And we'll talk about that, and we'll talk about what are some of the things you can do to help reduce that. Okay, so let's come up with let's talk about some sort of basic definitions. Okay, so we have, and these are just definitions. Okay, we need this again because we have instantaneous power, and then we're charging and discharging capacitor, so we need to look through energy, and then ultimately we want to come up with an average power for our circuit. So I'm just making the definition. So the instantaneous power, so there's a power as a function of time, is the current as a function of time times the voltage as a function of time. So that's the instantaneous power. Okay, energy is integrating the instantaneous power over some period of time. So if I look at energy, I would pick some period of time and I would integrate the instantaneous power as a function of time. That's the definition of energy. And then average power is this energy over the period of time over which I want to sort of get the average power. So it'll just be 1 over T, 0 T, T, T. Okay, so just to give you guys sort of the idea where we're going is, will be, because we're our transient power or switching power comes from the energy of charging and discharging a capacitor. We'll figure out how many times over some period of time will be charged the energy to charge and discharge that capacitor, and then we'll divide that energy by the same time period to get the average power consumption. But this is what we're looking for. And calculating the energy is an intermediate step. Okay, so again, hopefully these are reminders for you guys. Is if you look at the power consumption in a power supply, right? So we said generically, power consumption is the instantaneous current times the instantaneous voltage. But if you have a power supply, its instantaneous voltage is always constant and is equal to VDD. So if you just look at the power supply going to the CMOS inverter, this current will change depending on whether it's, so depending on what the circuit is doing, this current will change, but the VDD itself will stay constant. So this will be the change in, it's time dependent current on the supply, but times the VDD, whatever that is. So now this is just a definition of power on a resistor is just V squared over R. Okay. This is just from our basic circuits, or you can think of it as I squared R depending on, how you look at it. Okay, so the energy is, like we said, so let's say if you have a capacitor, right? This is where sort of power fails, because you're gonna put a certain current onto this, which gives you a certain voltage. Okay, so let's look at the different ways to look at this thing. So the Q is equal to CV for a capacitor. So this is, the charge, this is a voltage, this is a capacitance. So if you look at the voltage, it really depends on how much charge you've put on this capacitor. And basically the rate of change of this voltage, so dV dt, is dQt dt over C. So this is dQ dt is current, so dV dt is I over C. Or this says the reverse of this. But it's not a continuous power consumption, but it's a energy, because both current and voltage are changing as you're charging this thing up, but a single time where you charge or discharge this thing, you're saying what happens if I look at all the current and all the voltage change while I am charging or discharging this capacitance. So that's why in time you're going from 0 to infinity, because you're assuming it's one time where I'm charging this thing and I'm just going to do that, because I guess theoretically do it forever. It'll just the voltage will keep ramping up, and the energy going into the capacitor will keep going up. So that's why you're doing the 0 to infinity thing on when you're integrating with respect to time. Does that make sense? It's kind of confusing.
Yeah.
So let me
Yeah, that does.
Okay. Let me drive one more way, but let's say I got, I'm gonna have, what do I want to do? So let's say this is charge. Well, let me do this. Let's say I have a current going to a capacitor, and I'm just going to draw this voltage. So as a function of time, this voltage will keep going up, the voltage of that capacitor, because my current is just going to put, if it's constant current, it's just going to put charge in here and increase this voltage. But what happens is, if I have a maximum power supply, the maximum this capacitance will charge up to is the supply voltage. So it'll go to this value. So let's call that B sub C, the charge on the capacitor, or the supply voltage, whatever. Instead of keep going, it'll cap at this value. So even if I integrate sort of to time equal to infinity, I'll stop here. Okay, And then at this point, also by definition, there's no more energy I'm putting on this capacitor, right? Because if I was putting more charge on that capacitor, the voltage across it would go up. But once I hit my power supply, I just can't have it go any higher. So if I'm integrating sort of to plus infinity, means that if I look at it and integrating, and I could do the same thing by looking at integrating across voltage from 0 to V sub C. Okay, and change the integration from dt to dV. Okay, because these dt's cancel out. And I could look at this as being C dV, basically C dV VT. Okay, guys, so this dt cancels out with this dt, sorry. And I end up changing my limits and ending up with an integration with respect to voltage C V of t d of v. Okay. Now the max I can have over the limits for V of t, it goes between the max voltage VC and 0. So I basically just end up with this integral ending up being 1/2 CV squared. Does that make sense? Yeah, so this guy would be C, what is this, V squared over 2 from 0 to VC, right? So it'll just be C VC squared over 2. Yep. So basically, okay, after all that, sort of trying to prove it out, is we're saying, what this is saying is if I'm charging a capacitor from 0 to a voltage VC, one cycle of that charging or one act of that charging is going to need this much energy, 1/2 CV squared. So just going to remember that for now. And now let's look at, how how that affects, or what does that look like in terms of our inverter charging up a load capacitor. Okay, so we know that so let's look at just charging this capacitor. Okay, so we know that the energy required to charge this capacitor to this voltage is 1/2 the capacitor times voltage squared. We showed that here. So that's just the energy to charge a capacitor to a voltage. Okay, so that's the energy to store the capacitor. But we have a problem because that's not equal to what this should be equal to. Remember, this guy's off. So we're charging this guy up for the time being. So the total power, the total energy we pull from the supply is actually higher. Okay, and so it ends up being both let's see, what am I trying to say here? How would we lose that? That's because, okay, so now when your supply is constant, okay, so I'm gonna try, let me get this. So this gave us 1/2 CV squared because this voltage was a function of time. Okay, now let's say this voltage is not a function of time. So you're just looking at how much current you're pulling in from the supply. So the supply itself is a constant. So this energy would be C integral of 0 to VDD. And instead of V sub t, we'd have to plug in VDD dV. So this integral would end up being C VDD and then V from 0 to VDD. So it would be equal to C VDD squared, okay, which is this guy. So that's how much energy we're pulling from the supply. And the reason it's missing the 1/2 is because the supply is constant. And then the energy to charge up the capacitor is 1/2 of that. Okay, because the voltage across the capacitor is going up over that same amount of time. So it kind of makes sense to some, I guess if you want to think of it this way, is the capacitor is doing this where over this amount of time, whereas the supply is just doing straight that in some sense. So it's just constantly coming out. So basically what happens is we're drawing twice as much energy from the supply as we're using to charge up the capacitor. And the reason for that is that the other half of the energy gets burned up in the resistance of this P MOSFET. Okay, so you're gonna have, so over that amount of time, you're gonna have some power because there's this P MOSFET has a certain resistance and there's a certain current growing through that resistance. So if I integrate that power across that charging time, I end up with power lost in this P MOSFET as a result of charging the capacitor. It's basically as a result of the current going through the PMOS to charge up the capacitor. Okay. So that's the power coming out of the supply to charge up the capacitor. That's in the, when this guy goes from 0 to 1, you have this much energy is used to charge up the capacitor, and this much energy is used to pull from the supply. Okay, so this is when you get a 0 to a 1 transition. Any questions about that? I know that's kind of confusing, but no. Okay. Well, we'll have another graph that might help or confuse you more. Here it comes. So that's when you're charging up the capacitor. Now, when you're discharging the capacitor, this is kind of the interesting part, is that now remember this guy now, the PMOS is disconnected. Oops. So now this guy is disconnected. So I'm talking about when you're going from a 1 to a 0. So when you're discharging this capacitor, this guy's disconnected. So you're discharging this guy. Okay, so you're dumping that energy into the ground, but you're not pulling energy off the supply. So in this cycle of a 1 to 0 transition, there is no power coming from the supply. Okay, there's still heat dissipated, but that's the heat dissipated from that energy that you had stored on the capacitor and is dissipated in the NMOS, but there is no power coming from the power supply. Okay, so when you have a situation where you have a 0 to 1 and a 1 to 0 transition. So let's say this is a unit of time where you see a 0 to 1 and a 1 to 0 transition. That's all that happens in this period of time. And we want to look at the power consumption of that unit of time. You end up being, the total energy used in that period of time, or dissipated in that period of time, or pulled from the supply in that period of time, is this C sub L VDD squared, which happens right here. So that's the energy you've pulled from the supply during a rising transition. Half of it gets used to charge up the capacitor, and the other half is dissipated in the form of a heat in the PMOS. Then in this low going transition, we aren't pulling anything from the power supply, and we're just heating up this NMOS as it's discharging that energy that we dumped onto the capacitor. Any questions about that? I think the key thing is we're only taking this much on this rising edge and nothing from the falling edge. Okay. So let's look at the actual waveforms. This is kind of interesting for me. Always manage to confuse myself. But let's say we have a situation where we have a inverter, charging and discharging capacitor, and we have a 1 volt supply. This is the load capacitance, and basically the operating frequency is a gigahertz. Okay, so you basically, if you were sort of simulating this in Spice or whatever, you'd end up with this as your input waveform on VM. So this would be 1, because it should be really 1 nanoseconds. So that is a 1 gigahertz period is 1 nanoseconds. So in that period, you would have a falling edge and a rising edge. Okay, so as you guys saw in your project, our output, this is the output of this inverter, is gonna, when the input's low going, the output will go high. And when the input is high going, the output will go low. And you'll be sort of transitioning from, you'll be in some saturation output where you get a straight line. And then you'll get sort of RC when you're going to this is where the PMOS goes from saturated to linear operation. So it goes from a straight line to sort of an exponential settling curve. And this is where the NMOS goes from, linear mode, from saturation to a, give me 1 second, guys. I think my power consumption is low. Let me plug myself in. That wasn't staged for the power consumption lecture. Okay, so that's what the voltages look like. Now let's look at the currents first through the PMOS. This is kind of the interesting thing for me always. So in the PMOS, notice that when we're in saturation, we have like a current source in saturation. So it's a straight line. Current goes up. And this is when you reach kind of the full value of your saturation. You're sitting there. You have a constant current coming out of your current source. Okay, until, but the respite is brief, as they say, because, you know, then you get into the linear mode of operation. And then you get this reduction in current. So what you're doing here is you're going, so VDS, you're kind of, you're, you know, kind of going down this curve. You're in saturation, and then you get into this linear operation, and as the voltage, the voltage across your saturation doesn't matter so much. So that's why you get to this kind of a peak value. But when you're in linear mode, as your voltage VDS is being reduced across your transistor, your current is going down. Okay, so that's during a sort of when your PMOS is on. When your NMOS is on, it's doing the same thing, except it's in this part of the cycle. Okay, and then there's a brief period of time when they're both on. So you get this crossover current when, so like right here, when briefly both your NMOS and PMOS are on, and over here, again, when you get this sort of short circuit current when they're both briefly on. That ends up actually being a pretty small part of the power consumption, just because you're transitioning so fast. The amount of time where both of these guys are on at the same time is actually very short. Okay, so now if I look at the current that goes on to the capacitor, so this is this I sub C, it looks like, you know, there's no current until I get my PMOS current on it. And then the NMOS turns on and I have sort of a negative going current off the capacitor. So we went from here to here, looking at the currents. And now we basically go from currents to power. So in terms of, this is the power being used in the PMOS, the power burned by the PMOS. This is the power used up by the NMOS as during the discharge cycle. This is the power on the capacitor, and this is the power on the supply voltage. Okay, so now I think the key thing here is to just notice that there's only power consumption from the supply during the output rising transitions. Okay, and there's no power consumption. I mean, there's the crossover current here when both N and PMOS are on, but there's no power consumption from the VDD when we're discharging the capacitor, because the VDD is just disconnected from the supply. So then furthermore, when we calculate the energies, there is, when you look at the energy on the capacitor, we're charging and discharging the capacitor. So the net, sort of, there's a certain net energy being charged and discharged in the capacitor, but in the end, you don't have any energy left on the capacitor. But there's a certain energy you've basically pulled from the supply in this cycle. Okay, and that's energy, you just used it up, you just get it during this, again, during this output rising transition. And that's the energy used to charge up this capacitor. Well, that's the energy used to go through a full cycle of charge and discharge, because there was no energy during the coming from the supply during the discharge. I'm trying to think of what else to say here. Okay, so, the interesting thing in some extent, well, I still think it's pretty interesting. This also happens, by the way, I don't know if you guys take any analog CMOS circuits, but it like, so you get a similar weird effect. But notice that there is no, the size of these transistors is nowhere in these equations. Okay, so it doesn't matter like the resistance of these guys, the N and the P, nowhere in any of these equations. Okay, we're only looking at, when we're looking at sort of the power consumption here, we're looking at the following factors. We're looking at the capacitance that we're charging and discharging. We're looking at the value of the power supply, the VDD. Okay, again, just I'll refer you guys to this, to this equation. And we basically have, a unit of power consumption every cycle where we see a output rising transition. So this frequency is important because if this was, since this is a gigahertz, let's say this is a clock, right? A gigahertz means I get one rising transition every nanosecond. If this was a megahertz, I would get a rising transition every microsecond. So it'd be much fewer rising transitions, much less frequent. But again, the interesting factor is that the value, the width of these devices, as long as they're wide enough to charge and discharge this capacitor in this required amount of time, so you get a full transition one way or another, the actual values just do not come into anything. So the upshot is that, again, once you integrate all this stuff up, is the only thing that matters in power consumption and CMOS logic circuits are, the capacity, the load capacitance, the supply voltage, and the switching frequency. These could be large or small or whatever, it doesn't matter. This could be 10 times bigger than another circuit, as long as you charge and discharge both in time, it doesn't matter. So what else do I want to say that? So I'm gonna, this is like a very, very critical, very, very fundamental feature of the dynamic power consumption or switching power of CMOS circuits, is that it's entirely dependent on the capacitance you're driving, on the supply voltage and the switching frequency, and it has nothing to do with the the sizing, the resistance of these transistors. That's a little bit of a fudge, because we do have this crossover power current that is the power consumption when both of these guys are momentarily on, but we're assuming that it is the case, that that's such a small value that basically all our power consumption is charging and discharging this capacitor, and the resistances, the values of these two transistors do not matter at all. And the only thing that matters is this capacitance, the power supply, and the operating frequency. Okay, guys, I'll stop right there. And again, this is like a really, really fundamental equation and really important about why, CMOS is, well, it's a definition of CMOS, and it tells you a lot. And I'm going to go talk, about what this kind of tells us about how we can control our power consumption. Any questions, guys? If not, I'll let you guys go and we'll talk again on Thursday.
Thank you, Professor.
Thank you.
Professor.
Have a good one.